A be m by n matrix and Q be m by p matrix, then we have to show that first, column space of AQ is a subset of column space of A. Right? Second, column space of AQ is equal to column space of A if Q is non-singular. Right? Here Q must be non-singular. Let's take our A to be in the column format, that is C1, C2, C3. Now A matrix is of the type, yes, m by n. So how many columns are there? N. So writing this C1, C2, C3 up to Cn. And Q is n by p type matrix. So writing Q as Qij, and it is n by p matrix. Then let's take the multiplication of these two matrices. So writing A as C1, C2, C3 up to Cn, and writing Q in the matrix form as Q11, Q12 up to, yes, element present in first row. How many columns are there now? P columns. So pth column. Element present in the second row and first column. Element present in second row and second column. So on. Element present in second row and pth column. How many number of rows are there? N. Right? So up to Qn1, then Qn2, so on, Qnp. Right? So let's multiply these two matrices. So this is Q11C1 plus Q21C2 plus so on Qn1Cn, and then Q12C1 plus Q22C2 plus so on Qn2Cn, so on Q1PC1 plus Q2PC2 plus so on QnpCn. So what this shows? This shows that the columns of AQ are the linear combinations of C1, C2 up to Cn. So consequently, this lie in the column space of A. So therefore, column space of AQ is a subset of column space of A. Hence the result. Second part, to prove that column space of AQ is equal to column space of A, provided it is given to us that Q is a non-singular matrix. So let Q be a non-singular matrix. Non-singular means invertible matrix. And from 1 we have column space of AQ is a subset of column space of A. Please mark this as 1. Also, column space of A can be written as column space of A into the identity matrix, which is further equal to column space of, I can write this identity matrix to be equal to Q into Q inverse. Yes, can I write like this? Yes, because Q into Q inverse is equal to identity matrix. Why? Because Q is non-singular here, right? So this is further equal to, let me take this AQ together and using the first result, so here first matrix is the multiplication of A into Q, right? So column space of these two matrices, this is first and this is second, is a subset of column space of the first matrix from first part, right? So this implies column space of A is a subset of column space of AQ. Please mark this as 2. So from 1 and 2, what is 1? Column space of AQ is a subset of column space of A. And what is 2? Column space of A is a subset of column space of AQ. So from 1 and 2 we write that column space of A is equal to column space of AQ. Or column space of AQ is equal to column space of A, where Q is non-singular. Hence proof.